Hi, my name is Mike Moreno, and in this video, I'll explain how to make a monophonic subtractive synthesizer in Pure Data. Let's begin. So for this video, you will need the else library installed in your Pure Data distribution, or use Plug Data, which it has the else library already included. Let's create a new patch and make our master output. Here I'm going to make the out abstraction from else, which has a volume control implemented, and the scope object. So we can control the volume and see what we are hearing. Also, I'm going to do a multiplication of 1 into both left and right outputs of our system, so we can hear in mono, and connect it to the oscilloscope so we can see the signal as well. Let's change the scope to 1 sample per point, buffer size of 256, and a delay of 100 milliseconds so we can see our signals better. And let's do a simple test of a sine wave oscillator. Right there we can hear it and we can see it. Cool. So now let's begin programming our synthesizer. Let's start with the oscillator. I'm going to use a band-limited sawtooth oscillator, which basically is a sawtooth oscillator, just that it has almost no aliasing artifacts. So for example, compare this, let's put this at 10K, and you can hear a single 10K sound, 10 kilohertz sound. And if we change this to an aliased sawtooth, you can hear 2 tones, right? Which you shouldn't be hearing. So band-limited sawtooth works best for creating more analog sounds and synthesizers. Let's continue with implementing this into our MIDI controller. So here I'm going to do a note in, and we have 3 outputs. The first one is the MIDI note number, and the second is the MIDI velocity. But if we want this to actually work like a monophonic synthesizer, we would need a monophonic voice allocator, which is mono from else. Well, it's actually a voice manager, it says here. But let's connect our note and velocity here. And so this guy takes care about all the logic that's involved in playing the highest note of a on your key of your keyboard. And then we can do here, this is the MIDI note and this is the velocity. Let's comment this out, and I'm going to play a sequence so we can see it. This is the MIDI note, and the sawtooth first inlet is in hertz, so we have to convert this MIDI note into hertz. So in order to do that, we would need to use the MTOF object, right? And now this is in hertz, and we can see it in hertz, and we can actually hear it right now. Cool, it works. But if I stop playing the sequence, this thing will last forever, right? So we need a VCA along with a gate. So in order to convert this into a gate, we use this comparator that if it's higher than 0, then output 1. And so with that, we can actually mute and unmute our sequence. Cool. It works. So this is the gate, right? And this is our VCA, which if you multiply it by 1, it lets through the signal. If you multiply it by 0, you don't get nothing, right? Okay, moving forward to the envelope. So we can use the else ADSR envelope, and with the logarithmic flag, it will make the envelope more logarithmic in its curve, and therefore more natural and more similar to what you hear in analog synthesizers, right? So let's do 1 millisecond of attack, 250 milliseconds of decay, 0.5 sustain, half sustain, and around 500 milliseconds of release. So you can probably see these if you map or plot the envelope around this time. But let me here draw the comparison of the curves. So, for example, this one would be a linear envelope, which doesn't sound so natural. And let's do this here in right. So this one would be the logarithmic envelope shape, right? So it sounds more natural. These types of curves actually make it sound more like an analog synthesizer. So that's what the logarithmic flag does for the ADSR. So let's connect this here and let's play the sequence. Cool. There we have, this is the most simple one without the filter, but we actually do want the filter. So let's add the filter. Let me move this. Okay, so we'll start with here the low pass filter, which from ELSE, which is a 2-pole biquad low pass filter. 2-pole means it's around minus 12 decibels per octave. So that's the curve or the steepness it has. And we have 2 arguments. The first one is the central frequency in hertz, as it says here, and the second one is the resonance or Q or bandwidth also. So for example, let's do, I don't know, 1000 hertz and 0.7 resonance. And let's hear it. And then we can hear that it's a filtered sawtooth, right? But we actually want movement and modulation out of these sawtooth, right? So our hearing range is between 20 to 20,000 hertz. So we could actually make a V line here and do from 20 to 20,000 at the logarithmic curve, because that's how we perceive frequency in a logarithmic fashion. And then I'm going to label this cutoff, and we can actually connect this to a number box so we can monitor our hertz and use ELSE's float to signal, which converts float to signal, and a ramp time about 20 milliseconds. So we don't hear clicks when we change this parameter. Right, let's play this. Oh my God. Of course, that one happened. There we go. Now we can actually move this cutoff and etc. Problem is, this is linear modulation, even though the slider is set to a logarithmic curve. This doesn't enable exponential or logarithmic frequency modulation, which is something that we would want in a type of synthesizer like this. So I will first clip our cutoff to between 20 to 20,000 hertz, because that's why we heard the pops at the beginning. It was because we were at 0 hertz, and so that creates a feedback loop and just clips the audio, right? Right. So 20 to 20,000, and you know what? We'll delete this cutoff. We'll make a new one, and we'll leave it like it is, from 0 to 127. No logarithmic curve, and let's do cutoff here. So this is a really interesting trick I've learned, which is if you use MTOF, this one actually provides a logarithmic curve for the frequency, and you can also do exponential frequency modulation, right? So let's hear it. Also, the control from the cutoff is way more natural, right? So say, for example, we want to use this envelope as a modulation source. Well, it's easy. We should only use here a plus sign and then duplicate this. And this one would be, it's no longer the cutoff. This one is going to be the envelope amount, right? So now this is the envelope amount. And let's do here a multiplication here and this one over here, and it sums over here, right? So basically, let's hear it first. And we can hear the modulation right from the envelope. What's going on here? Why am I using MIDI to modulate the frequency? Well, as I explained, the MIDI to frequency object with a tilde enables exponential frequency modulation. So, for example, if this envelope amount is set to 12th, it will modulate an octave, just an octave, right? Because it's 12 semitones, so 12 semitones equals to an octave. And if I go 24, it will do 2 octaves, right? So compare this to how you would usually do it in a linear fashion, and linear frequency modulation doesn't sound as natural. It's more digital. So exponential frequency modulation is where it's at if you want to emulate a virtual analog synthesizer, right? So yeah, that's more or less the explanation for that. And finally, let's make a control for the resonance. So this one, I will put this here, and let's change this one to a logarithmic curve. Let's do from 0.4 to, I don't know, 7. And by the way, always initialize your sliders. Otherwise, your pad, you will need to initialize them every time you open the patch label. Let's do resonance here. Resonance, there we go. And finally, since we don't want to clip our system, let's use a soft clipper distortion for our output. So this one is a soft clipper distortion. This one will basically distort everything that goes after 1 to -1 to 1. So, and it sounds better, right? Cool. And now we have a simple monophonic subtractive synthesizer. Well, we could also add the ADSR controls over here. Just be careful with the sustain. It needs to go between 0 to 1. The rest of the controls are in milliseconds. So let's just add the attack because that's a really noticeable one. I'm going to make here a number box object, which is basically a number box, which you can initialize here. And we're going to do initialize, yes, label attack from 1 to, I don't know, 1000, which is a second. Okay, and we can hear its effect. Cool. And there we have it. By the way, this clip is so we don't clip again. This is prevent clicking, more like prevent clicks from the low pass filter, because if you go past 20,000 hertz or below 0 hertz, you will get really clicking sounds. So that's it for this video. I hoped you enjoyed it and it is useful information for you. All right, happy patching.